Salam and welcome everyone. So today we're going to be doing the question on the screen that says, suppose that 2.5 millimole of a perfect gas molecules initially occupies 42 centimeter cube at 300 Kelvin and then expands isothermally isothermally to 600 centimeter cube. Calculate the change in Gibbs energy for the process. So the first thing you have to know is to write out your parameters. We're told the number of moles is 2.5 millimole um, of perfect gas molecules initially occupies 42 centimeter cubed. So that means we have the initial volume to be 42 centimeter cubed at 200 Kelvin. Okay. And then expands isothermally. So we have an increase in volume. So there's going to be a V final to 600 centimeter cubed. So this is an isothermal expansion problem, meaning the temperature is going to be constant throughout the entire process. So we're told the temperature is 600 Kelvin, okay? And of course, the change in temperature is going to be zero. And we're asked to actually solve the change in Gibbs energy. Now, I have solved a very similar question, but that took a lot of time. Now I'm trying to solve it to take less time. So make sure you watch how I solve this question with this method, and make sure you watch the other video in the description box to see how I solve it with the other method. So the first thing you have to note is all of that, what I've written. The next thing you know is that for a question that involves isothermal Gibbs energy, we have this general formula, which is just simply GM, okay, of the final pressure, okay, equals to GM, so the molar Gibbs energy of the initial pressure, okay, plus RT ln the P final divided by the P initial. So with this method, we're not going to actually go find the value for the initial pressure or the final pressure. We're going to use our understanding of the initial volume and the final volume, as well as our knowledge of the combined gas law. So the combined gas law is just P1, okay, V1 or P initial V initial divided by T initial equals P final V final divided by T final. So because our temperature is going to be the exact same value, we're going to erase that. So we're not going to be using this. So what we end up with is P initial, V initial equals to P final, V final. So what's next is that for us to be able to manipulate this equation to what is going to be easy for us, we're going to actually put V initial and V final in terms of P final divided by P initial. So P final, okay, divided by P initial becomes V initial divided by V final. So we're gonna, when we have this particular information here, we can just simply substitute here since we're dealing with an isothermal problem anyways. So that's basically how it's done. So let me like fill this in. I apologize, my pen mistakenly erased this. So now we have this. So let me rewrite in the formula. Now we have the molar Gibbs energy of the um final volume, okay, is going to equal the molar Gibbs energy at the initial volume, okay, plus RT ln V initial, okay, divided by V final. Now, we were asked not to find the molar Gibbs energy. We're not asked to find the change in molar Gibbs energy. We were told to find the change in Gibbs energy. So rewriting this, we have, let's say, GM, okay, of V final minus GM of the V initial, okay, equals RT ln V initial divided by V final. So that would be change in GM. So yeah, change in GM is just going to be RT ln V initial divided by V final. I apologize, but this first part of the work just involves a lot of math. It's to make our eventual formula that we're going to be substituting our values into to be very, very easy for us to calculate with. So now you have this. Because we're asked to find the change in Gibbs energy and not the change in molar Gibbs energy that we have to apply our knowledge that the change in molar Gibbs energy is the same thing as the change in Gibbs energy divided by the number of moles. So to go from to go from changing GM to changing G, we just simply cross multiply and we have the change in G to actually be the number of moles times the change in molar Gibbs energy. So the change in G of M. So because of course, we have an equal to here, we have to multiply this number of moles by this equation. So let's imagine this is equation one. Just bear with me. We're just gonna multiply, okay, equation 1 by number of moles. So when we do that, we end up with changing G, okay, changing G, which is what we're trying to do here, okay, is now going to equal nRT ln V initial divided by V final. That is basically the equation that we're going to use now to solve this question. So the next thing you have to do, of course, is for you to simply substitute. We have 2.5 millimoles. So we have the change in G becomes 2.5 times 10 to the power negative 3 moles, so millimoles, times 10 to the power negative 3 moles, times, we're going to be using the gas constant, 8.3145 joule per mole, Kelvin, because the change in Gibbs energy would have to have the units in joules. So we have to use the gas constant that matches the unit of what we're solving for, which is a change in Gibbs energy. So that times the temperature that we're given, going back to our question, we see our temperature is 300 kelvins. So 300 Kelvin times ln V initial, we know that to be 42 centimeter cubed, and we know V final to be 600 centimeter cubed. So 42 centimeter cube divided by 600 centimeter cube. Of course, we cancel out the mole, the Kelvin, centimeter cube, centimeter cube. And some of you may be wondering, why didn't we like convert centimeter cube to the proper volume unit for a question like this? Well, because we're just dividing by two different volume, the initial volume and the final volume, and we're not actually multiplying what is inside the ln with any other information like pressure, temperature, number of mole gas constant. This is okay because we're just dividing by volume, so we're actually gonna have the correct answer. It's just like you saying, why don't I divide 1000 grams divided by 2000 grams? Well, 1000 grams divided by 2000 grams is 1 over 2, but guess what, 1 kilograms, which is equivalent to 1000 grams, divided by 2 kilograms, which is equivalent to 2000 grams, would also give me 1 over 2, because we're just dividing within the same exact information parameter, which is the volume. So this is not an issue, because I know sometimes they confuse chemistry students and they ask me that question whenever I'm tutoring. So just simply having changing G is just 2.5 times 10 to the power negative 3 times 8.3145 times 300 times ln 42 divided by 600. We end up with 6.2358 joules, okay, times ln 42 divided by 600 is just 42 divided by 600 is just simply 0.07. So changing G, just 6.23588, okay, times ln 0.07 will end up giving us negative 16.5828 joules. So this is basically the answer to our question. But as chemists, we have to make sure that we have the proper number of significant figures based on the information in our question. We have 2.5 millimole. So 2 sig figs, 2 sig figs, 3 sig figs, 3 sig figs, and the lowest number of significant figures based on the numerical values in our question is 2 sig figs. So we have to approximate this answer here in two significant figures. So we have the change in Gibbs energy is going to actually be negative 17 joules. So if you have any questions, please put in the comment section. If you have any concerns or suggestions for what I should cover, please also put in the comment section. I'm a tutor who helps students in all your STEM related courses to succeed and to improve. I also help with student mentoring for any of you that may be struggling. Don't hesitate to email me at shuhabitutoring@gmail.com. I wish you guys all the very best. Assalamu alaikum wa rahmatullahi wa barakatuh.